In the past couple of videos, we talked about the idea of why chemical bonds form to make chemical compounds, and that's us looking at lower energy states. And then we spent some time talking about electron dot notation with valence electrons to determine how the atoms were going to bond to each other. We haven't talked about their arrangement in three-dimensional space yet, but that's actually a little ways down our list right now. We need to just take a closer look at Lewis structures, maybe get into some polyatomic ions, some non-octet structures, meaning we break the octet rule, and then look at things like resonance and formal charge and bond order. Now, we need to simplify things, so we're going to jump backwards a little bit and say, what were the skills we needed in order to be able to draw these structures? And the first skill we needed was to be able to look at the periodic table. I'm not going to lie, my wife was making fun of me because she saw this periodic table, and she's like, oh, we can afford a much better periodic table than that. So I just printed a new one out. I hope you're all impressed. So there is the new periodic table I printed out. It's the exact same thing, it's just not dirty and chopped up. All right. So looking at the periodic table, what's our goal in looking at the periodic table? We need to get the symbol, and I don't even know that that's something that I should write as a step, but the two things we're getting there really, we're going to get the chemical symbol, and we're going to get the number of valence electrons. If those words scare you, that's going to be our number of dots eventually, and we're getting those based on group number on the periodic table. All right, so that's from group number on, and I'm going to abbreviate periodic table, all right? The group number on the periodic table. And those are up here. Group 1, 1 valence electron, 2, 2, 13, 3, etc. All right. Other skills that we needed last time, we needed to be able to count 8 to get our number of valence electrons and draw dots, and then, I guess drawing dots, is that a skill? Connect dots. All right, our goal eventually was like we want 8 valence for each atom, and that is our octet rule. All right, and octet, again, in the big picture, it's not just 8. We had discussed that in the one video, but S holds 2, P holds 6. Those are valence sublevels. That's a total of 8. But some things like hydrogen and helium don't have a P sublevel, so 2 electrons would be a full octet there. These are our skills. You don't have to really know anything about chemistry, other than I can read this, and I can count to 8, and then I can connect some dots. And that is the basis for our structures. There's a few things that I want to make very, 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 very clear right off the bat, one of which is a few things that I glossed over as we were making the other structures, all right? So when you're starting out, we need to look at the periodic table, find the symbol, count the valence electrons, and I wrote this as kind of a footnote on one of the pages, but it's worth having it written out on a clean sheet of paper that when you're drawing the Lewis structures, you're going to start with the element with lowest electronegativity, well, in the center. And of course, there's one big exception to that, not hydrogen. Hydrogen only has one bonding location. It can't be the center of anything. All right, so hydrogen's never going to be in the center. And sometimes as I'm doing these examples in class, someone might point out like, oh, isn't that really the thing with the most potential bonding locations? So I'm going to write that down. I think it's kind of an interesting idea. It's the element with the most potential bonding locations. And I'm not saying that either of these rules is written in stone, but once you get the hang of these, it literally is just connecting the dots and stop trying to outsmart yourself. And by potential bonding locations, we're talking about single dots, right? And I think that this is glossed over very often, like why are these things the things that are in the center? And the short answer is it has to do with sharing, all right? Things with higher electronegativities are better at attracting electrons, so they're going to be worse at sharing electrons, right? And in the big picture, you'll hear me use this terminology over and over, and this is not super legit chemistry terminology, but what I'm talking about is things that are stronger, right, versus weaker in this tug of war. So covalent bonds involve sharing of electrons. Ionic bonds involve this give and take of electrons in a tug of war over electrons. All right? So it is not that they are stronger or weaker. That's just a way to say that this is better at attracting electrons. It has a higher electronegativity. And I'm going to abbreviate electronegativity to save some time. This weaker is lower electronegativity. And what does that really have to do with anything? Well, electronegativity developed by Linus Pauling were largely based on electron affinity. So saying something has a higher electronegativity is saying that it has a larger energy benefit to gaining an electron. So it is better for the system energetically to gain an electron for things that have higher electronegativities. So maybe, and just to make some numbers up but for reference, so for example, if we look, fluorine has an electronegativity of 4.0, all right, versus carbon, which has an electronegativity of 2.5. So which one of these things is better at attracting electrons? Fluorine, all right? Why? Because fluorine will, philosophically speaking, pay more for an electron. If we look at actual electron affinity values, and these are rounded quite a bit, but fluorine has an electron affinity of around negative 330 kilojoules per mole. And I want to point out that those numbers, or those words, don't have to mean anything if you haven't watched those other videos, but that's a larger in magnitude number than carbon, which has an electron affinity around negative 130 kilojoules per mole. All right? So both of them, carbon and fluorine, it is energetically advantageous for them to gain an electron, but fluorine, it is much more advantageous. In fact, like again, stepping on this terminology a bit, fluorine is willing to pay much more for an electron, so it's the thing that gets the electron. It won't have to share, whereas carbon isn't willing to give as much and it'll end up sharing. All right, and I know there's a lot of stepping on, energetically favorable and not, but that's the basis. Why are the things with the lower electronegativity in the center? The atom in the center is going to have to do the most sharing. It's going to bond to the most things, right? This is paying 330 kilojoules per mole of electrons, right? Versus this that's paying 130. This is the one that's going to have to share to make things work out. And often we see that in terms of the number of valence electrons, right? Fluorine has 7 valence electrons, group 17 on the periodic table, versus carbon, which has 4. Not only is it more advantageous for fluorine to gain an electron, it only has one bonding location, right? And those two things are tied together. The closer to a full octet it has, the more beneficial it is to gain one electron, all right? This has 4 potential bonding locations, and it has a lower electron affinity. So what I really want you to pull out of all that is the idea that your lowest electronegativity is going to be in the center, all right? And you could also, if you wish, think of that in terms of the thing with the most potential bonding locations. Those things are related because of the way the electron affinities work out. Either one will work. And that's the rule we're going to be using for the Lewis structures.